Okay, it's noon. I'm required to start class. So, wow, 20%. Not even a quorum. Well, precious few that have arrived. What is there anything? Questions you have? Anything before we start?
When is our next test?
The 7th of November. So today's the last day for this material, and the Monday I'll do a review like I did last time. So, is there a calendar app on this thing? I don't know. Oh, there's a calendar. There we go. So, there on November 7th. So here we are. We're going to finish today the stuff. Probably go into chapter 8 a little bit. So 29th and 31st will be in chapter 8. And then 5th of November will be a review. Test on the 7th. And then the 12th of November is a holiday. Then we have the 14th, 19th, 21st. And then the 3rd and the 5th. So we're running out of class days. I think the final's on the 12th, if I remember correctly. So, other questions? Okay. So as we left off, let's talk about the orbital shapes. And if you do the radial distribution function, if you look at the 1s orbital especially, you actually have a little bit of electron density in the nucleus of an atom. So this is why there are some differences in isotopic electronic structure, is because of this effect. And now, so quantum mechanics, if you study more things, things that are discrete, so like quantum mechanics, they are so because of boundary conditions. So you can take a rope and attach it to the wall, and you can whip it back really fast. It's pretty easy to do like this, like a jump rope kind of thing, if you ever played jump rope. If you whip it faster, you can get an area in the center where it's kind of where the jump rope or whatever you have, there's an area where it just sits there. This is what's called as a node. And the node is in an electron cloud, it's an area of 0 electron density. So as the electron at a certain point is not there whatsoever, and that's called a node. And if you see these nodes, for instance, the 1s orbital has no nodes. The 2s, though, has a node. So if you here's the picture of the s orbital. They are spherical, and there's the probability distribution function, the psi squared, and the shell model. You have a little bit of this is the 2s in there. The y-axis is the probability, x-axis is the distance. There's a small peak and there's a bigger hump. This is where the electron tends to hang out, but there is a node right there. So, and the 3s is going to have 2 nodes. So maybe you can start to notice the number of nodes is the principal quantum number minus 1. So let's look at the s orbitals. Let's talk about the p orbitals. Let's first look at the distribution function. The p orbitals have a node at the origin. So there's not nearly as much electron density in the nucleus of an atom for the p orbitals. S orbital is much more pronounced. And if you remember if we have the p orbital, so if L equals 1, n sub L can be minus 1, 0, and 1. What that happens, there's 3 orbitals. And this is the 2 p's. So these here are the 2 p's. And also, just starting off here, let me talk about the sign of the wave function. S orbitals are always positive. P, though, have a positive negative sign to their wave function. So p's, d's, f's, and so on, even higher than that, g, h's. But we're not going to talk about g's or h's in this class. Someone asked me that after class. but we can go higher than F. Those do have positive and negative sides, and that's going to be important when we talk about bonding in chapter 10. So here is the d orbital, and there's 5 of them. You have the dxy, the d yz, the dxz. They're all just the planes. So if you have the coordinate system, one is this way, one is this way, one is this way, and they're diagonally. They're in between the axes. And then you have the dx squared minus y squared orbital and the dz squared. These two are important because that's where metals bond. They bond with these 2 orbitals. So at least most of their bonding. You can bond in other ways, but that's where the simple bonding happens along these orbitals. Here are the f orbitals, and they're just kind of funky shapes. The shapes aren't that important, but I think they're cool. That's why I put them in the lecture. And I already talked about the phase of the orbital there, positive and negative. That's important for bonding. Atoms mostly are spherical, so let me illustrate why they're spherical. Well, let's look at a couple. Let's look at a couple electrons right here. So we have the s orbital. It's just plain old sphere. Then we have the 3 p's, like so. Then we have the d's, right? We have the z squared. That's a funny looking one with a donut. Then we have the x squared minus y squared. Then we have the that would be the xy. Let's do the xz. Then we'll do the yz, like that. And you can see they all kind of jumble up, just with my kind of hand drawing there. Atoms more or less are spherical. It's because if you bring them up, there is a little bit of structure and density to them in a funky shape, but they are roughly spherical in shape. So, anybody have any questions of this? So we're done with chapter 7, although the shapes are not on the test. So really, last class was the end of it. But we are going to have to move on, though. This stuff is not on this test. Okay. So let's talk about periodic properties. I already mentioned the different orbitals. So with the angular momentum column number L, if L is 0, s orbital, L is 1, p orbital, 2, d orbital, 3, f orbital. So what I'm doing now I'm going to start what's called the Aufbau principle. That just means building up in German. So for hydrogen, we write its electronic structure is ground state electronic structure. Ground state means lowest energy as 1s to the first power. The superscripts, they tell you how many electrons are in those orbitals. That means there's 1 electron in the 1s orbital, and denote this with an up spin. And it can be plus or minus 1/2. We just put up just because we're very positive in chemistry. It could be downspin. And helium has 2 electrons, so we denote this as 1s squared, and then we have an up and down arrow for the electron density. The electron. So that just denotes one is spin up and one spin down. And we mentioned the Pauli exclusion principle last time. No 2 fermions can have the same set of quantum number in the same atom. And one thing, so that's the reason why we have to have spin up and spin down. We can't have them all be spin up in the 1s electron. And we talked about that. That's why matter has structure. And for hydrogen atoms or hydrogen-like atoms, the 3s, 3p, 3d, 2s, 2p, all the same n principal quantum numbers, these are known as degenerates. That means that they're all the same energy level. Of course, degenerate has a negative connotation for us colloquially. Like, you guys are a bunch of degenerates. It means you're all the same. It usually means you guys are all ruffians or something like that if you want to use old British terms. You could all be degenerates as well. You could all be amazing, awesome students, and I hope you guys are degenerate in that fashion, right? But degenerate means all the same energy. So, but atoms have more than 1 electron, have the electronic field and the magnetic field affect the energy levels. The electronic field affecting the energy levels, this is called the Stark effect, and the magnetic field affecting the energy levels of electron is called the Zeeman effect. So for atoms, it's much more involved in the Zeeman effect. For bonding, molecular orbital Stark effect is much more pronounced, at least for things around the bonding. And Coulomb's law, if you haven't seen this before, the electronic field is a constant times the charge of one charge a second over the distance, and the force between them is the distance squared. So that's what is drawing the electron towards the nucleus, is the fact that an electron is negative and the nucleus is positive. So now let's talk about some other things, shielding and penetration. So if you have an outside electron, we're going to talk about this soon, an outside electron is called a valence electron. If there's inner core electrons, the electrons on the inside shield the charge of the nucleus from the other ones. But if you look, for instance, here, the 2s orbital has this hump that's close into the nucleus. We talked about that just in the last chapter, just 10 minutes ago. Because of that, you can have an effect called penetration, where the shielding is not complete. It's not like it's a complete shield. Okay. So I mentioned the building up principle. You don't have to do all the calculations. This is from a non-hydrogen atom energy level diagram. So hydrogen atom, the different ends would all have the same energy. So like for 2s, you would have 3 2p's, and the 3s, the 3p's, and the 3d's would all be the same energy. But for non-hydrogen or hydrogen-like atoms, this is what it looks like. And then the electrons populate by this process. So here's hydrogen, here's helium. Then I'm going to go lithium is number 3, beryllium is number 4. Now I'm going to go on to boron, and then now we get to carbon. So carbon, I can either put the electron here like this, or I can put it here like that. And what do? You put it in the different orbital. And you also put it as parallel spins. You put it like this, you do not put it like that. Have parallel spins, it fills the orbital first. This is known as Hund's rule, H-U-N-D-S, Hund's rule. And electrons then populate in this fashion. And now, so one electron is boron, carbon, nitrogen. So oxygen, now they start to pair up. Oxygen, fluorine, neon, like so. Okay, so let me go back to the Hund's rule. I've seen it called a few things. One of them is called the bus seat rule. Like if you're sitting on a bus, you usually pick a seat that's open. That's partially true. One of the issues with that, though, is that when electrons pair like this, it releases something called the pairing energy, which is actually fairly significant. So it's a combination of the attraction for the pairing energy, and the other is just it doesn't like to be around a negative charge. In this case, it's a combination of things. It's more or less that it doesn't want to be around a negative charge. So there are some energy. In certain cases, this would be more energy favorable. And those cases tend to do with nuclear stuff. So nuclear things, the pairing energy is more significant than electrons. Okay, now let me back up even more. So here with boron, let me go even back. Okay, beryllium, here's beryllium with 4 electrons. All the electrons are paired. This circumstance is known as diamagnetic, meaning that there is no external magnetic field associated with a beryllium atom. A boron atom, though, with one unpaired electron here, this is known as paramagnetic. So a boron atom does exhibit an external magnetic field. Same thing with carbon, same thing with nitrogen, same thing with oxygen, although nitrogen is more, same thing as fluorine, and then neon now is diamagnetic because all the electrons are paired. So, and this is a common misconception with students. Paramagnetic and diamagnetic have nothing to do with reactivity. So fluorine is paramagnetic. It is extremely reactive. Gold is paramagnetic. It's extremely unreactive. Neon is diamagnetic. It's very unreactive. Calcium, so here's calcium. Calcium is diamagnetic. It's extremely reactive. So the reactivity of something has nothing to do with its magnetic properties. So, and then now this is just the Aufbau principle. Like I said, you build up by adding electrons, parallel spins, and then adding on, and then you go to the lowest energy. Now, something to note with the 4s, and these are the relative energies. You don't have to memorize these. But notice that the 4s then is lower in energy than the 3ds. So the 4s will be populated before the 3ds. Also, when you remove electrons, electrons are removed from the highest end first. So this case where I've put 5 electrons in the 3D, the 4s electrons are removed. So in ions, those electrons are removed. So I'll go over this more in detail soon, but I just wanted to mention it all here with this chart. So I've already mentioned this. Paramagnetic means one or more electron is unpaired. Diamagnetic is all paired. So you see here, lithium has one unpaired electron, it's paramagnetic. Beryllium, 2-paired diamagnetic. Boron has one unpaired, it's paramagnetic. Carbon, 2 unpaired, paramagnetic. So now this is different than ferromagnetic though. So there are only a few elements that are ferromagnetic. So that doesn't mean, so aluminum, for instance, is paramagnetic. But if you put a magnet up to aluminum, you'll notice it just drops to the floor. So at least at this temperature and pressure, well, more temperature, aluminum is, as a bulk material, is diamagnetic. So keep that in mind. Atomic properties do not necessarily extend to bulk properties for these cases. So we're only talking about the atoms. And I already mentioned all these through that. Okay. So let's see if you're following. What is the ground electron configuration for sodium? And sodium has 11 electrons. Which one do you think is the ground electron configuration for sodium? How many think it's A? How many think it's B? I think it's C. I think it's D. No one's following. Okay. So where are you guys getting stuck? What are you guys doing? You guys are obviously not understanding. Where are you getting mixed up? This is where we have a conversation, right? I explain things. You learn them now. I know that you're not learning it, so I have to understand why you're not understanding it. Is there a part that's fuzzy? Okay. So what are your thoughts? Oh, you guys want to talk to each other? All right, let me come around. Yes. Yes. All right. Okay. So S. That's one of those 2 electrons.
Yeah.
like that.
Six.
Oh.
Two orbitals of two each. So if you look at A, there's 7 electrons, and P, it's 2 one's wrong. And C, the 3 is 11, there's 2 electrons. So that's the D. It's okay, but in the ground state, so you have the 2s1 and 3s2 of the D, that's possible in the same excited state. So it's,
Why is it B? Oh. Okay, opposite can be C.
okay, so each orbital can only hold 2 electrons. So the S's, an S orbital has 1 orbital, can only hold 2. So because of that, this 3s11, that's wrong. And the P's can only hold 2 apiece, and there's 3 P's, so it can only have 6. So the 7 is too many, it's not that one either. So you have to choose between B and D. And if you look here, there's 2s1 here. This is known as an excited state. That's an excited state. That's possible, but that's higher in energy than this one. This one here is the lowest energy one. That's the ground state. So, questions with this? Okay. All right. Now, much of these rules I'm going to talk about really only apply for the S block and the P block. It gets a little more complicated for the D block. Although this valence is true valence, so I need to go back and talk about what's valence. Valence means outer electrons. Core means inner electrons. So I like to describe it using clothing. So for instance, a hydrogen atom with 1 dot here. So the dot, this is also known as a Lewis diagram. We put electrons as dots. Electrons are not dots, they're fuzzy clouds. Okay, but hydrogen has 1 electron, 1 dot. That's like someone with 1 item of clothing on. So it's like a woman in a 1-piece bathing suit. Then helium here has 2 dots, 2 electrons. It's sort of like a woman in a bikini. So top and the bottom, 2 things, nothing else. Now lithium has 1 outer electron, but it has 2 core electrons. This is like a woman wearing a bikini wearing a trench coat. Okay, so the coat covers up the bikini. You can't see the bikini. You can only see the trench coat, so it looks like the person is only wearing 1 item of clothing. But on the inside, there is 2 items of clothing. So, and then beryllium would be like a bikini underneath, a coat, and a hat. And then 1 glove, 2 gloves, right? So you can kind of see the things. And then I don't know what would be after you get a complete shell, something covering all that. So you can't see anything except for the outer electrons. So that's hopefully my clothing analogy can help you there. It's the idea is that electrons, they only see the outside. So whenever there's going to be bonding, only the outside electrons matter. The inside electrons, the core electrons, do not matter. They matter to the atom, but they're not up for being shared with the other atoms. So hydrogen has 1 valence, helium has 2 valence. Now lithium, you notice something though, these families here, we organize them that way. So hydrogen, although it's kind of in a category of its own, lithium, sodium, potassium, rubidium, cesium, all have 1 electron. And then the alkaline earths, they all have 2 electrons. We organize the periodic table by its electronic structure, by the number of outside electrons. And the noble gases, helium is kind of in this category by itself, but the rest of the noble gases have 8 valence, 8 outer electrons. And this has led to the octet rule. So we're going to talk about this with bonding. Things tend to bond to the number 8. And Lewis, the person that came up with this idea, he was right about the octet rule. He was wrong about the reason. He thought atoms were like boxes, and then the 8 came from the 8 corners of a box. I know this is rectangular prism, but imagine it was a cube. There are 8 corners of a cube, right? So 4 up top, 4 on the bottom. He thought that's the way atoms were, and he drew bonding and atoms that way with the cubes. He was right about the number 8. I keep on saying 4 corner. Oh wait, 8. He was right about the number 8. He was wrong about the reason. So the reason, of course, is because of the 2p's and 3p's. And that's real. We really have s and p orbitals. We can see them using scanning tunneling microscopes, STMs. So, but in general, things when they bond, they tend to bond to be like mutable gases. Okay. So here are some electronic configurations. Right. Okay. Now let's go beyond that. Let's write the electron configuration for germanium. So germanium is right under silicon here. So what is the electronic configuration for germanium? Oh, and here's the periodic table right there. You can write the complete electronic configuration. To do that, you can start this way: 1s squared, 2s squared, 2p6, 3s squared, 3p6, 4s squared, then we go 3d10, 4p2. And germanium, like I said, is right here. And when you go through, here's the 2s there. I'm sorry, 1s, 2s, 2p, 3s, 3p, 4s, 3d, 4p, 1, 2. That's where you get that, use the periodic table. You can also do a shortcut. You can notice that this is the configuration for argon, and you can write argon's configuration. Oh, and argon's not there, sorry. Argon is here. You can write argon 4s squared 3d10 4p2. You can only do that when you put in the electron configuration. You can only do it for noble gases. Can't do it for anything else. And then identify the valence electrons. I'll put it in yellow. They are the 4s2 and 4p2. The valence electrons are the highest n only. So what about the 3d10? That's considered core. So the 3s, that's still less than 4, so the d electrons are going to be considered core. So how many questions? Does it make sense? All right. And this, you can use the periodic table this way for doing electronic configurations. The first 2 columns are the S's. The 6 on the right are the P's. The transition metals are the D's. And the rare earths and the actinides are the F's. So let's figure it out for selenium, although I used it already for germanium. Germanium is right here. But the configuration for selenium, you can take argon's configuration over here, and then look at the 4s2, 4s2, 3d10, and then 4p, 1, 2, 3, 4, like so. So do you see how I've used the periodic table this way? Questions with that? All right. Now let's see how you can follow. So, what is the electronic configuration for phosphorus? Phosphorus is right here. You should be able to figure it out just from this. There's logical fallacies in all of them except for one. How many think it's A? How many think it's B? Okay, actually most classes are going for B. B is the right answer. So, does anybody want to explain? Raise your hand. Okay, good job, you're following. You guys look like I feel like I'm talking to a graveyard today. It's not even Halloween yet. So here is the power of the quantum mechanical model. The number of valence electrons dictates properties, specifically chemical properties. So, and sometimes the columns are called families. Here's a picture of my immediate family. So there's me on the right, and then there's my brother and my 3 sisters, and my mother and father. And if you look at us siblings, you can see that we're all big and blonde. So we definitely look like we're related. And there are many similar properties. So if you look at the alkalis, they're all very reactive. But here's a picture of my father, my brother, and my nephew, all John Allen Fergusons. And I have my dad with gold, my brother with silver, and my nephew with copper. So, and they're all in the same family. And you're like, well, they don't even look alike. Gold's yellow, silver's silvery, it's like how most metals are, and copper's red. How are they similar? They're similar because they don't react. They don't react very much. So copper tends not to react. Silver reacts a little less, gold reacts even less. And also these metals are expensive. Copper is cheaper than gold, of course, but they're expensive. And there are some similar physical properties. They conduct electricity very well. So that's why we use copper wiring instead of aluminum in our houses, because it's more likely to catch fire if you use aluminum. Silver is the most conductive of all the elements, but we tend not to have silver wiring because silver is just too expensive. So, yeah, so we even name the families: alkalis, alkaline earths, and halogens, noble gases. And also, not surprisingly, similar families have similar charges. Alkalis all get +1, alkaline earths +2. If you're wondering why beryllium's not there, beryllium is just extremely toxic, and we tend not to use it, so we don't want people to get sick. And okay, now we're going to talk about atomic trends, so periodic trends. First one we're talking about is atomic radius, so how big an atom is. And the trend is that this direction it gets bigger, and this direction it gets bigger. So the further to the left and the further down, the trend is to get bigger. So why is that? So now remember, electrons just see the outer electrons, the inner one's shielded. So lithium has 3 electrons. Its positive center has 3 protons, has 2 core. So the one outside electron sees a +1 center. Okay? Then you go to beryllium. Beryllium has a +2 center, effectively. So what happens is the lithium is a big, big atom, and then the beryllium, the 2 electrons say, ooh, that's a +2 center. I'm gonna get closer. Boron, the +3 center, electron crowd shrinks. Carbon, nitrogen, oxygen, fluorine, it's shrinking even more. So then neon is a really tiny atom. The smallest atom, size-wise, is helium. Helium is the smallest. Also, as you go down a column, the electron cloud gets bigger. So lithium is a +1 center, and has the electron in a 2s orbital. Sodium has a +1 center, effectively, because it's shielded by the other electrons. The other 10 electrons shield the 10 of the 11 charges in its center. So the 1 electron in the 3s orbital is just further out. So lithium is kind of big and fat. Sodium's bigger and fatter, as is potassium, as is rubidium. So the biggest element is francium while it exists for the few seconds that it does. So francium and cesium, cesium is just above francium on the bottom left corner of the periodic table. They're very, very big atoms. And then as you move across the periodic table, generally speaking, they get smaller. You can see the rules don't hold true necessarily for the transition metal series. So these trends, it's a general trend, but it's not an exact trend, but it works very well for the S and the P block. The other thing, we're going to talk about electronegativity soon. So when you have electronegativity is the ability for an electron to draw, the ability of an atom to draw electrons to itself. Like, have you ever gone to a party and there's a really attractive person there? Some of you notice there's like a circle kind of forms around those people. Like, oh, that's a really attractive person. I'm going to go watch that person. So they have the ability to draw people to themselves. That's what it is for atoms as well. And instead of people, it's electrons. And the atoms that can draw electrons to themselves, those are known as electronegative. The most electronegative atom is fluorine. Why not helium? Why not neon? They're noble gases. They don't care. They don't want more electrons. Fluorine, on the other hand, wants one more electron. And if you compare fluorine to lithium, so fluorine is a tiny atom with a +7 center. Lithium is a big atom with a +1 center. So attractiveness, Coulombic law, is charge of 1, charge of 2, divided by distance squared. So a +1 versus a +7, the +7 is more attractive. And then the size, since fluorine, if you look at the size here, fluorine is 72, I think it's a picometers or something. And lithium is 152. So fluorine is less than half the size. So it's less than half the size and it's 7 times the charge. So that's the reason why fluorine is so good at drawing electron density itself, because it's a tiny atom with a very positive center. And this is going to become important in bonding. I'll talk about this later on with bonding, because you can get unequal sharing of electrons. That's called a polar covalent bond. And you can also get polar molecules, where you have molecules that have a positive and a negative end to it. And fluorine is like an electron vacuum cleaner. You pop that on a molecule, it's going to draw up a lot of electron density. So here's this picture up here is just put into a different picture. So this just shows you there. And then the alkali metals are always at the top, and the noble gases are always at the bottom in terms of size for each period. Period is a row. Okay. And so let's use this logic. So on the basis of periodic trends, choose the larger atom. So carbon or fluorine. So carbon is here, fluorine is here. Fluorine is to the right, fluorine is smaller, so larger atom here is carbon. Are you understanding the trend? Or you can say carbon's to the left, it's bigger. Make sense? Okay, carbon or germanium. So they're in the same column. So as you go down a column, the atom gets bigger. In this case, germanium is below it, so it's the bigger atom. Questions with this one? Okay, let me change colors. Nitrogen or aluminum. So nitrogen is further up and it's further to the right, so it's smaller. Aluminum is further left, it's further down, therefore it's bigger. So aluminum is definitely bigger. So, questions with this one? Now we have aluminum and germanium here. Germanium is lower, so it should be bigger. Germanium is also further to the right, so it should be smaller. So in this case, you don't know. And I think germanium is bigger. Where is it? Aluminum, germanium. Oh no, aluminum's bigger. So you can see here, actually, you have to look at the data, and aluminum and germanium, in this case, actually, aluminum is the bigger atom. But you wouldn't be able to know unless you looked it up. So, questions with this one? Okay. And I mentioned diamagnetic or paramagnetic already. Electrons take them highest end first. And the magnetic properties of atoms have nothing to do with the reactivity. Okay, so let's talk about ions. We're going to write the electronic configurations for each of these and determine if the ion is diamagnetic or paramagnetic. So aluminum's ground state, maybe I should write the ground state in blue. Ground state here is going to be, let's get the periodic table. I don't have it available. Okay, so it's aluminum is going to be neon's configuration 3s, 3s2, 3p, 3. It's 3p1, I'm sorry. 3p1, and it's plus 3, so it's going to be neon's configuration 3s0, 3p0, and neon's configuration is 1s squared, 2s squared, 2p6. And then since if you look at the 1s, 2s, 2p3, these are all paired up like so. And because of this, this is diamagnetic. So do you understand what I've done here? I have the ground state of aluminum, rip 3 electrons off, look at the electronic configuration, everything's paired, therefore it's diamagnetic. Questions on how to do this? All right, sulfur. Let's go on and do sulfur. Well, sulfide, I should say. Sulfide. Sulfur is just over more. It's under oxygen. So sulfur is just right here under oxygen. And that's going to be neon's configuration. So here's neon. It's going to be 3s2, 3p4. So neon, 3s2, 3p4. Then we have plus 2 electrons because it's minus 2. So add 2 electrons. So we're going to have neons, 3s2, 3p6. And of course, that's going to be argon's configuration right here. So sulfur bonds to be like argon with the octet rule. And just like instead of the 2 s's that I've drawn over here with aluminum plus 3, the sulfur is going to have all the s's and all the p's paired up. This is diamagnetic. So, questions when I do this one? Just add 2 electrons. Okay, iron plus 3 is going to be a little more complicated. And iron's configuration is going to be argon's. So we have argon's configuration 4s2, I think it's 6. Let me see. Iron. So iron is right here. So it is argon's configuration 4s2, 3d, 1, 2, 3, 4, 5, 6. So there we go. That's its ground state. Now we have, I should put minus. So we're going to lose 3 electrons, and we're going to have argon's configuration. So remember, highest end first, so 4s0, 2 electrons there, 3d, 5. And then the Ds, there's 5 of them, and 1 electron in each. So iron plus 3 is extremely paramagnetic. In fact, you can have iron plus 3 that's a permanent magnet. That's known as magnetite. So iron plus 3 is paramagnetic. So, like so. Questions with this? All right, students always get this wrong. At least, so I had a test question on this, and 2/3 of the students got it wrong. So then I said, I'm going to ask you this on the next test, and then 1/3 of the students still get it wrong. So are you guys going to be the 1/3 that gets it wrong, or maybe the 2/3 that get it right this time? Well, yeah, I hope so. This class is pretty good. This semester, both sections, you guys are doing very well. So hopefully everyone gets this concept right. So pay attention. This is known as isoelectronic atoms and ions. So isoelectronic means same electrons. So iso, same, electronic. So sulfide has 18 electrons, chloride has 18 electrons, argon has 18 electrons, potassium has 18 electrons, calcium plus has 18 electrons, potassium plus 18, calcium plus 2, 18. And if you look at the size of these atoms or ions, so sulfide has 18 electrons but 16 protons, so same, but 17 protons, 18 protons, 19 protons, 20 protons. Which one's going to be the smallest? It's the one with the more positive center. So same number of electrons, if something has a more positive center, that atom or ion is going to be shrunk. And the negative anions, these tend to be bigger. So this is what happens. If you take an atom and you give it an electron, what happens to it? It blows up. Okay? It gets really big. What happens to an atom when you take an electron off? It gets smaller. So ripping electrons off makes the ion small. Adding electrons to atoms will make the ion bigger. Expands the electron cloud or contracts it. And the level of expansion or contraction depends on the positive center. So, which one is bigger? Which one is bigger, sulfur or sulfide? So because this has the extra electron density, sulfide is bigger. So because sulfur has 16 electrons and 16 protons, sulfide has 18 electrons and 16 protons, it gets bigger. Calcium, same thing. When you rip off electrons, it shrinks. So calcium metal is got a smaller atom than the calcium ion. And then here we are with bromide and krypton. Bromide and krypton, they both have the same number of electrons. It's not 18. What is it? Geez, where did I put my periodic table? Oh, here we go. So we have, okay, 30. So here's bromine and krypton there. They both have 36 electrons. Bromine has 35 protons. Krypton has 36 protons. They have the same number of electrons. Which one's bigger? It's the one with the less positive charge, the 35 protons. So, back down here. Which one is it? Which one is the larger? It's bromide. Because same number of electrons, weaker positive center. That's why it's bigger. So, that's the one that everyone gets wrong. Well, they used to get wrong. So remember this and get it right. So questions of this? Okay, first ionization energies, next trend. So Remember we talked about radiation, ionizing radiation. How does something ionize? Rips electrons off. So how easy it is to rip an electron off is known as, so if it's easy, it's a low ionization energy. If it's difficult, it's a high ionization energy. So think of it like a relationship. So how hard is it to break off a relationship for two people that have never met in real life? Let's say you're a Tinder match and after you match, you never met the person moves to Singapore. You think, like someone said, you know what? If you never contact that person again, I'll give you $20. How likely are you to take that? Yeah, probably pretty likely. So maybe you're like, I really like the person, $100. All right, fine. What about if you are in a huge relationship with a person, you have a house, you've got kids, you've got a dog, you own a couple cars together, and now you're like, all right, that Tinder match, you let go for $100. How about this partner? You let it go for $100? No, you're gonna need a lot more money for that, right? So same thing with electrons. There needs to be, to rip, how do you rip off an electron? Add energy. So adding energy to the electron, if enough energy is added, the electron will fly out of the atom. So, for instance, here, hydrogen needs 1312. I think it's probably kilojoules per mole. Yeah, it is. Ionization energy, kilojoules per mole. So you need that much energy to rip off an electron from hydrogen. Now you look over helium, moving over to the right, what's happening? Helium is getting smaller, and it's a positive center, so more positive center. So helium is a smaller atom and has a +2 center. Hydrogen it's still a small atom, but it's bigger than helium, has a +1 center. So it's much more difficult to remove an electron from a smaller, twice as positive center than a bigger +1 center. So the trend ionization energy is opposite the size. So the further you are to the right, the further up it's higher. And that's exact opposite of the size. So moving down the periodic table, it gets lower, and to the left, it gets lower. There's an exception right here. You can see that there's an exception for nitrogen and oxygen. Moving over to the right, nitrogen is a higher ionization energy than oxygen. And that trend continues for phosphorus, for arsenic, but it doesn't work for antimony and tellurium, and bismuth and polonium. So we have a switcheroo, but why is that? Well, the idea is that it's easier to rip this electron off here than here because the electron on oxygen is paired with another electron, and it's easier to rip it away because of the Coulombic repulsion. So the negative charges not liking each other. They rip away more easily. So that's more of an exception to the rule. You can see it's not a set rule. And again, chemistry is an observation science. I'm just reporting what is observed. So I can explain why, but the trends are not always smooth. These are general trends. You don't have to know the exceptions. Okay, so let's do this for on the basis of periodic trends. Which element has the higher first ionization energy? Aluminum or sulfur? So here's aluminum, here is sulfur. Sulfur is further to the right, therefore it's bigger. Then arsenic or antimony. So arsenic is above antimony, therefore it's bigger. So nitrogen or silicon. Here's nitrogen, here's silicon. Nitrogen is further to the right, and it's higher, so nitrogen is bigger. And then oxygen or chlorine. Here is oxygen, here is chlorine. So oxygen is further up, it should be higher. Chlorine is further to the right, it should be higher. We don't know. We can't tell by periodic trends, we have to look at data. And it turns out oxygen. Oxygen is the right one, but we wouldn't know that by periodic trends. We have to look at data. Questions with this, with the logic? These are the kind of questions that you find on like the MCAT and the GRE. So at least not the chemistry GRE, but the MCAT you will, because it's a logic question. Okay, is that it for there? Okay. Last slide. So electron affinity. This is the energy released when an element absorbs an electron. And there is absolutely no periodic trend to this. No periodic trend whatsoever. And some of them are positive, some of them are negative, actually. And even noble gases, like you think noble gases shouldn't bond, but some of them have electron affinity. So you add electrons to noble gases, they will have an electron affinity. So this is something, not everything has a periodic trend. Electron affinity is some of them. As an example of one. And, oh, and here's metallic character. I don't like this trend. It's my own personal opinion because it's not something you can put tangible-wise. So what is a metal? What are metals good at? Metals are good at conducting. They're good at losing their electrons. The most conductive element I've already mentioned is silver. Does that mean silver is the best metal? Well, you define it that way. But silver conducts, so does carbon. Carbon conducts heat, and diamond conducts electricity, and graphite. And the DNA molecule has no metals in it whatsoever, and that conducts electricity. So what do we call a metal? What do we call a non-metal? So what does make sense, though, is if you look at, like, say, boron and aluminum, since aluminum is underneath boron, it's more metallic-like. Also, if you look at it over here, so nitrogen and phosphorus, definitely non-metals. Arsenic and antimony, they're kind of metals, they're kind of metalloids. And then bismuth, definitely a metal. So that trend works there. And also, if you look at like selenium and gallium or bromine going this way, it certainly gets more metallic going that way. So I can kind of see the argument for it, but I just don't like the trend because does that mean that francium is the best metal? Does that mean that helium is the best non-metal? So you can use it to determine kind of like, oh, well, these are more metallic than these. But that's about the only thing you use this trend for. But I'm kind of an exact person when it comes to that. So, but that's in your book. And questions like that are not on the final or the midterms. Chemical properties. So I told you can predict these things. Much of these I already told you. Alkalis, they're one valence electron, very reactive. Alkaline earths, also reactive, but also tend to be insoluble. Halogens, very reactive. Halogen means salt-forming. Noble gases tend not to react. So, all right. And I'm kind of done for this chapter. Anybody have any questions? You know, and hopefully you guys seem to be following the stuff, but you guys look like you're kind of bored. Oh, well. What if I let you go 17 minutes early today? Oh, now you're sitting down. Oh, I'm just kidding. I'm going to talk for another 16 minutes. No, you guys are, that's a good place to stop. I'll let you guys go. So, if anybody has any questions, come up and see me. And I will stop recording.